Today we're doing section 3.2, day 2, and we're going to be talking about some more properties on logs. So we're just going to kind of work on evaluating, and then we'll kind of come to what the properties are for today. So if I set this equal to x, I put this in exponential form. So I have 7 to the x equals 7, and it's implied that there's a 1 there, therefore x equals 1. Whoops, sorry. So we set this equal to x. So I have 5 raised to the x equals 1. So a property that we know is that anything raised to the 0 power equals 1. So I could rewrite this as, 5 to the x equals 5 to the 0, because 5 to the 0 is the same thing as 1, and then you could see you have the same base, therefore x equals 0. For letter C, again, we're going to start by setting equal to x. My base is 4 raised to the x, and then this whole thing, this 4 to the 5th power, would go over here as the argument, so therefore x equals 5. And again, we're now going to go opposite way. We're going to put this in log form because I'm in exponential form. So I have log. My base will become 6 of x, and then the exponent, which is what it's equal to, is log base 6 of 9. Therefore, I can determine that x equals 9. So now that we kind of went through four problems, we're just kind of sum up some common properties. So the first log property we would say is if I have log base b of b, it's always going to be equal to 1. So if these two numbers match right here, the answer will always be 1. Similarly, if I have log base b of 1, it's always going to be equal to 0 because I can never raise b to any power other than 0 to get the result of 1. My inverse properties would be this, like the second two. So if I have log base b of b to the x, the answer will always be what that exponent was. And then if I have b raised to log base b of x, again, the answer will always be x. And again, these are kind of common sense, and it's not like you have to memorize them. You can always figure them out by putting them in the equivalent form. So some common log, if I have log base 10, the answer will always be 1 because it's implied that this base right here is 10. And same thing with natural log. If I have ln of e, the answer is always equal to 1 because it's implied that there's a base of e right there. All right, so now we're going to go back and do the word problems. So the magnitude R on the Richter scale of an earthquake of an intensity I is given by R equals log I divided by I naught, where I naught is the intensity of a barely felt 0 level earthquake. The earthquake that destroyed San Francisco in 1906 was 10 raised to the 8.3 times as intense as a 0 level earthquake. What was the magnitude on the Richter scale? So we have this equation. I have R equals log. So the I is the intensity, and they're telling you the intensity was 10.8.3 times one that was felt on a 0 level intensity. And in the denominator, I have 0 level intensity. So the I to the 0 level intensities are going to be canceling out, and I'm going to be left with log of 10 to the 8.3. And using those properties, we know that the base is 10 here, therefore the answer is 8.3, and that was the magnitude for that earthquake. So next example. When the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The bar graph in the figure shows the temperature increase throughout the hour. The function f of x equals models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 50 minutes. How well does the function model the actual increase shown in the figure? So Because I want to know 50 minutes, you're simply going to plug in 50 into the equation. So we're evaluating this at 50. So I have 13.4 ln of 50 minus 11.6. Obviously, this is calculator work, so you would just type this in the calculator, and we'll get approximately 41 degrees Fahrenheit. Now, that's after 50 minutes. That's how much it has increased. Now, the question wants you to compare it to the model. And notice that 50 minutes, the temperature is 40, so you would say that this matches well. Okay, so the function matches the data, basically, is what they're saying. All right, that's all for today.